Thermodynamics is a branch of physics, being based around the work, heat, and energy affecting a system. There are three laws of thermodynamics, which is what this presentation will be about, being labeled zeroth, first, and second law. Thermodynamics as a whole first began being utilized in the 19th century, when scientists were first discovering how to use and build steam engines. Thermodynamics is important to us in our daily lives simply because it is used in almost every device we use day to day. Heating and cooling systems, engines, and architecture use thermodynamics in their designs to minimize waste of power. At its creation, thermodynamics was used to help us use power most efficiently, or to keep a house heated without requiring much fuel. Important vocabulary to remember during this presentation are, first and foremost, heat and temperature. These two can be intertwined sometimes, but do remember temperature is related to how hot or cold an object is, while heat is the flow of thermodynamic energy. Thermal equilibrium, which is when two separate objects meet and their heat spreads between the two before becoming equal. And finally, entropy, which will be covered later. Some important variables to remember are specifically work, which is energy transferred between objects, energy, which is the capacity to do work, and heat, which is energy transferred through temperature, mostly being used in energy 2 minus energy 1 equals heat minus work. Another variable used is P, which is used to denote pressure, and capital T, which works for temperature. Another, maybe not as useful, thing to remember is the different variables for heat, like Fahrenheit, Celsius, and kelvins. Kelvins are the least familiar to us, so for a basic explanation, the Kelvin scale was named after a man called Lord Kelvin or William Thomson, and it is used far less in either Fahrenheit or Celsius. It is not expressed in degrees and rather uses itself, saying something like 3 kelvins rather than 3 degrees Kelvin. Kelvins are used mostly in physical sciences and also in lights. Something like an old incandescent light bulb would produce about 3,000 kelvins, which is 2,726.85 degrees Celsius and 4,940.33 degrees Fahrenheit. The way to convert from kelvins to Celsius is to subtract 273.15 degrees from the kelvins unit you have, and to get Fahrenheit, do the same but multiply by 9/5. For a fun fact, the reason absolute zero is called what it is, despite being far into the negatives for both Celsius and Fahrenheit, is because it is exactly 0 in kelvins. To give a little bit more background, I'll go over the history of it slightly. The first modern thermodynamic theory was developed in 1850. At that time, rather than thermodynamics, it was referred to as moving force of heat. The theorem was developed by Rudolf Clausius, due to him not believing that heat could be completely converted to work without any other changes. He introduced a law that heat does not flow cold to hot. In 1851, William Thomson introduced the noun thermodynamics, and introduced a second law, that heat was not entirely converted to work. Before work and heat were recognized as quantities of the same type, there were three main ways people perceived them. One being that work produced heat without any true meaning to the words, with fire outside of the picture. The second being fire and heat being the same idea, with a substance called phlogiston, which had mass and was released upon being burnt, and other ideas with similar parts. Finally, there was the idea that fire and heat were separate entirely, with massless conserved heat fluid. This was the one many people believed in for the longest time, being called the caloric theory. Of course, later, all these ideas were obsolete. In 1660, Robert Boyle, with the assistance of Robert Hooke, created the design of a vacuum pump, which allowed the study of gases at different pressures. This furthered the understanding of heat quite a ton. In 1669, Ambience studied the properties of air under temperature and pressure changes, which helped him discover that the change of pressure divided by pressure equaled the change in temperature. In 1703, he discovered absolute zero, being about 240 degrees under 0 Celsius, which was later corrected to 273.15 degrees below Celsius. From here, I'm going to skip ahead a tad to 1865, which is when Clausius first coined the term entropy, as well as many other terms like virial, ergol, and disgregation, the latter two being replaced with potential energy and entropy units, respectively. Although when entropy was first discovered was earlier than that, being in 1854, but was only named in 1865 and could not be determined by a direct measurement. Now for a brief covering of the laws of thermodynamics. Firstly is the zeroth law. This law was mostly discussed earlier in the description of thermal equilibrium, but for a little bit more of an in-depth explanation, thermal equilibrium is when two objects or systems of separate heats meet together and balance out, becoming the same temperature for both. Then, the first law. The first law is also referred to as the law of conservation of energy, meaning that if energy is lost in a system, it is simply given to either a different system or the environment around it. This is something we've seen in class before, but rather than with heat, it was with energy. Like how potential energy is turned to kinetic, and kinetic energy is transferred into the environment due to friction.
Alright, I have found a FET lab, actually, that can help show some things. So, you may have seen this probably in chemistry or earlier in physics class. I'm pretty sure we actually use this in physics. I don't remember. But as you can see, when you rub them together, they shake a lot more. And that's because the friction generates energy in the form of heat, as you can see here. And that is mentioned in but yeah, see how whenever it gets to a point in the heat and speed of the friction, the rough surface goes away because the heat has caused the molecules to burn off, and that's pretty neat in my eyes.
And finally, the second law. The second law of thermodynamics is entropy. Entropy can simply be defined as a measure of how much thermal energy per unit of temperature is unavailable to do work. It can also be a measure for the disorder or randomness of a system. It is used to tell the difference between reversible and irreversible changes, such as how heating up a pot is reversible, as it will simply cool back down to its original temperature, while melted ice will not simply just return to a solid due to a slight change in the system. Even if only one part of the system is irreversible, both contribute to increasing the entropy in a system. Something that is always irreversible is a spontaneous change, such as gas being let into the atmosphere, or, once again, ice being melted. The Clausius definition of entropy makes the formula delta S equals Q divided by T, or entropy equals heat divided by temperature above absolute zero. Now, for a brief section on the Joule's pedal wheel experiment. For the longest time, people agreed with the theory of heat being a liquid, so in 1841 to 1842, a scientist by the name of James Prescott Joule wanted to test that theory, with an experiment where he had two weights on strings and pulleys where they were connected to paddle wheels inside an insulated container of water. Due to the wheels spinning, they created friction, which generated heat. This experiment was important as it brought us today what we understand heat is, not as a liquid, but rather as an energy. He claimed to have been able to measure temperatures within 1/200th of a degree Fahrenheit, which is what caused skepticism at first. Although later, some recognizable names, like William Thomson, or Lord Kelvin, had backed his work. After death, due to the advancements his many experiments had brought to science, the Queen of England had granted him pension, and his gravestone was inscribed with the number 772.55, which was his most accurate measurement of the mechanical equivalent of heat. A more recent event in the thermodynamics field, and I specify in the thermodynamics field because it was noticed in 2013, is how qubits in quantum mechanics make faster decisions at cooler temperatures. This ties into the physics concept as at higher temperatures, more of the molecules in the qubit would end up working worse due to increased entropy. A real-world application of thermodynamics you would see in your day-to-day life would be with refrigerators. Refrigeration uses the law of thermodynamics that states hot flows to cold, using refrigerant coils inside of the fridge to absorb the heat contents inside of it to cool it down. That's why some fridges, when you touch the side of the door, it may feel hot, as it had recently absorbed heat from the contents inside of it.